All right. Yep, I'm Jamie Sullivan. I'm a finishing PhD student at Berkeley. And here I'm going to, in this very short talk, give you an overview of the idea of what Zach Lee, my collaborator, and I have been doing to embed neural networks in ODEs for linear perturbation theory. And I only really have time, sorry, to explain what this title means. So let's start with a brief review of linear perturbation theory in less than a minute. Well, what are we doing here? Basically, we're taking linear fluctuations and seeing how they evolve in the picture that we're all very familiar with, where we have the metric coupling to everything, the neutrinos, dark matter, dark energy, etc. And then you have a stiff ODE system because the electrons, protons, and photons are, of course, also coupled to each other in the early universe. And we're doing this with our Boltzmann code Bolt, which is in Julia. It's differentiable. I could give a 40-minute talk on this, and I obviously don't have time to do that, so I'll cut myself off here. But the idea I want to talk about today is how we might be able to discover the presence of new physics at the linear perturbation theory level. So you might think if you have some new species with some new coupling, you could do the thing that we always do. If you have some a priori model for how this should behave physically, you add a blob to this thing here, you add some connections, which are the coupling between different species, and then you do your analysis. But what we're doing now is thinking about doing this in a slightly more data-driven way. And instead of adding a new blob with terms where you say, oh, this is sourced by the metric and couples to other things, I'm going to now say I'm going to let any arbitrary linear coupling be in the ODE for my new species, which I'm just writing as delta here, and its time derivative is given by this. U contains all of the other perturbations, baryons, photons, etc. And here, this contains coefficients in time and in space parameterized by wave number. And at the end of the day, once you've fit the neural network weights and biases through a power spectrum or whatever downstream observable you have, you will have some reconstructed neural network in the space where the physics is really actually happening in the couplings of the ODE. Okay. And it's important that this is not a general neural network on the right-hand side, as you might have for something like a neural ODE, because we want to not break linear perturbation theory. So it's just some coefficients of a linear operator. And, oh, I'm already almost out of time. Incredible. Flash talk. And this is very sad because I have this nice animation that shows this actually working, where it's fitting downstream in this somewhat contrived test where we're able to actually have the neural network, when we solve the ODE that it gives us, it goes right through this line with some noisy data here. So I'll post this animation in the Slack underneath this talk. But the kind of end goal of this project is just to give you a different view of what the data is telling you. And when you have this reconstructed neural network, you also want some sort of uncertainty quantification. And then if you're a model builder, you can take this neural network with uncertainty quantification in the ODE and then just try and spend more or less effort in regions where the uncertainty is high or low for that particular data set. You look at multiple different data sets. And I think this will be increasingly important as we go to more precise data sets in the future. Thanks.
Great.